If you're watching this video on geometric sequences, it would be useful if you watch part 1, how to do geometric series part 1 first. So we've looked at two series so far, one that went 2, 6, 18, 54. The first term was 2, the common ratio was 3. There, each term is bigger than the previous one. The second one we looked at, we said the first term was 4 and the common ratio was a half. We didn't bother working out what the numbers were, but I'm going to do that for a minute. First term was 4. The next one will be 4 times a half, which is 2. The next one will be 2 times a half, which is 1. The next term will be 1 times a half, then a half times a half, and so on. And the numbers we get are getting smaller and smaller. Where the numbers are getting smaller and smaller, what happens is we call that a converging series. And we can add these up in a slightly different way to these up here. If we add these up, the total we get, by adding all of these numbers up, the 2, the 6, the 18 and so on, the total we get will get bigger and bigger the more terms there are in the sequence. Eventually it will just get hugely big, in the millions and billions, and it will just keep on growing and growing. But here, if we add these up, well, let's just see what happens. We've got 4 as a total so far. Add on 2, we get 6. Add on 1, we get 7. Add on a half, we get 7 and a half. Add on a quarter, we get 7 3/4. That's the same as 7 6/8. Add an eighth on, I'll get 7 7/8. If I added the next one on, which would be 1/16, well, 7 7/8 is the same as 7 14/16. Another 16th would take me to 7 15/16. And this totals here, all of these numbers here, our totals, are converging. They're getting closer and closer to some other number. They're not getting massively different. Here the totals would have been 2, add 6 is 8, add 18 is 26, add 54 is 80. There, that total is just getting bigger and bigger and bigger. But here, it's not getting massively bigger each time. It's getting a tiny bit bigger. And actually, this total, this running total, is getting closer and closer to a specific number. This happens if the common ratio, R, is a number smaller than 1. If it's a 0 point something number. And it can be a minus or a plus 0 point something number. So actually R can be between -1 and 1. So it can be either plus or minus 0 point something. If that is true, we get a series that converges. And it actually means we can add up an infinite number of terms. Because each term is getting smaller and smaller and smaller. The next one will be 1/32 and 1/64. We can actually add these series up forever. And we get the sum to infinity. So the symbol down here is infinity. So that means the sum to infinity. And there's another formula we use if we're summing a geometric series to infinity. It's A divided by 1 minus R. There's no mention of n anymore because we haven't got a fixed number of terms in our series. We're going forever. And it's a much easier formula to use. So if we look at the sequence we've got here, which starts off with a 4, and the common ratio is a half. I'll just write that down again. We've got A is 4, and R is a half. Well, the sum to infinity, using the formula here, is going to be A over 1 minus R. 4 divided by 1 minus a half is a half. 4 divided by a half, how many times does half go into 4? It's 8. So what we're saying here is if we carried this on and kept adding and adding, eventually we would get to 8. Actually, we should be saying we would tend towards 8. You never quite get there, but it tends towards 8. And if you did it for infinity, we'd say, well, you actually get 8. So this formula here for the sum to infinity is another formula that you need to learn for geometric progressions. We're now going to look at another example. This question we've got for a geometric series with a first term of 12 and the common ratio of 2/3. Find the fifth term, that would be U5. The sum of the first 8 terms, that's S with an 8 down here, and the sum to infinity. We're going to use the rules we've had earlier. the fifth term, u5, well, a rule we had earlier was that the nth term is a times by r to the n minus 1. So the fifth term would be a times by r to the 5 minus 1, or a r to the power of 4. So that would be 12 times by 2/3 to the power of 4. And if we get our calculator and have a go at that one, 12 times by, put it in brackets to make sure the calculator does it in the correct way, 2/3 to the power of 4. Calculator gives me an answer of 64 over 27. And if I wanted it as a decimal, it's giving me 2.37. That's the answer to 3 significant figures. So I've done the first bit, U5. The next bit, it said the sum of the first 8 terms. Again, I had a formula before. The sum of the first n terms was a into 1 minus r to the n over 1 minus r. Substituting the numbers in, 12 is a, r is 2/3, and I have to do that 2/3 to the power of n, which here is 8. And 1 minus r will be 1 minus 2/3. So that's doing my substituting in. And again, if I go for my calculator, I'll do the bracket first. I need to do 1, take away a fraction, 2/3 to the power of 8. I need to times that by 12. And I need to divide by this. 1 take away 2/3, that's 1/3. So I need to divide that by 1/3. If I do that, I get an answer, and I can convert it into a decimal. That will be 34.60. Again, to 3 significant figures, it would be 34.6. I'll be consistent to 3 significant figures. That's that part of the question done. Next part of the question was the sum to infinity. And I can only do the sum to infinity because my r, my common ratio, is a 0 point something number. It's 0.6 recurring. I can only do the sum to infinity if the common ratio is either plus or minus 0 point something. And the formula I had for that was a over 1 minus r. A here was 12, r was 2/3. 1 minus 2/3 is 1/3. 12 divided by 1/3 is the same as 12 times by 3. That's 36. So I've now found that if you're kept on with this series forever, the sum of all the terms would be 36.